Okay, in the previous video, I um discussed this LET concept and summarized the whole lectures in Python, as well as I demonstrated them using ABAQUS environment. And in detail, I discussed the um, relationship between the LET theory, a biharmonic function, and the trend of the stresses and deformations using ABAQUS and Python. Now, this next lecture, I have changed the contents and I found the new contents very interesting. If you are working with um, flexible pavements, so it's not about flexible pavements. If we only discuss the flexible pavements, we actually consider the top layer. So what about the layers beneath, because it's a multi-layer system. So in that case, okay, just before proceeding, if you are watching my course, I have some free resources here on my GitHub profile, in which the first one is the Python generated asphalt materials, and the second one is ABAQUS batch job submit script. So these two are free tools which you can use if you are watching this course. So make sure you download them, and I will try to discuss them as well. Now in this module 6, I will discuss the pavement de-stress analysis using ABAQUS. So I will discuss this with a practical project with demonstration and ABAQUS, right? So I think I need to I need to cover this in the next lecture. Now I'm going to cover the module 7. So module 6 will be covered in the next lecture. And this module 7, soil models and ABAQUS, especially when you are working with flexible pavements. So in multi-layer system, if you are using a single layer, that's okay, but that doesn't make sense, because there are some thumb rules which I discussed in the previous lectures as well, which you need to consider. So let's go to a brief discussion by opening ABAQUS, and I think this project. So we are going to discuss this project in the context of what we are doing there. Let's go to load, and in the load we have this tire passes. So let's suppose you are working with your ABAQUS file, right? And you are trying to discuss things there, right? So what are some of the key understanding that are required when you are working with the layers, materials definition, and other stuff in dynamic loadings, etc. So I will, in general pattern, try to discuss them, right? And then I will start a practical project. But before that, I will go to this freestyle cycle lecture as well. So let's go to the material properties, right? Our first main focus is material and soil models. So let's call it materials and soil subgrade instruction. So we can also call it material choice in pavement analysis. So let me change this to material choice. Yes, this would be fine. Right, and here the first thing when you are working with your ABAQUS flexible pavement file, you need to select which soil model you are going to use in many layers. For example, at this time I have base, subbase and subgrade in my project, which I already have defined for the case of simplification. And you can see I have these properties assigned to my model. By the way, if you are working with the asphalt concrete or the top layer, you can find this tool on my GitHub repository. So you will find out this tool, and this work for stress relaxation data. I have developed this in Python, and it will help you a lot in material modeling for the asphalt concrete, right? Anyways, go back to our lecture. So if you are working with ABAQUS and you are trying to model materials, right, material properties, and let's say you are working with subgrade model. Let's suppose you are working with a subgrade model, and you need to define the properties. And why would you define those properties in your ABAQUS simulations, right? So in order to carefully discuss this, the first thing which you will come in your mind is the definition of the soil model, because it's only related to soil. And you can see we have various kinds of layers for subgrade and subbase. If you have a very good computer, you can do a versatile simulation using a more realistic project for the properties definition, but that will cause a lot of problem for you in terms of computational cost. So the first thing that you need to do is the definition of the soil model and ABAQUS, right? So you can idealize the soil using different constitutive models, and most of the time if you study the literature, you will find out that the linear elastic is the simplest but most reliable soil model idealization and ABAQUS when it is adopted in literature review. So the thing is, we can consider it elastic for resemblance with linear elastic theory model and results, but the problem is soil actually exhibits nonlinear behavior, especially under large deformation. So a question may arise in your mind that you have, let's suppose, selected a elastic model, right? So what would you do if you consider it elastic? How would you justify your model for this choice of material? Well, another question may arise: if I am doing it with only elastic data, why don't I use an actual soil model, right? So for that, another question arises in your mind. There are various model of soil, right? And if you check them, for example, if you look at here, in plasticity, we have, let's suppose, Mohr-Coulomb plasticity model. So why don't I select this one? And what will happen if I select this model using these parameters, right? And there is also a question: if we are, for example, if we are using a solver approach, let's suppose we are using a solver approach here, which is a viscous approach here. What would happen if you use static general analysis? And what if you are using static general analysis? Why would you select the properties that has nothing to do with my simulation, such as density? So maybe you will need soil step definition, another step definition, to consider the other environmental impacts and the physical phenomena that occur in the soil. If you want to do that, such as consolidation and compaction, then you would need the density to consider the gravitational impact on your project as well. So it's kind of an extended scope of your project that you are going to decide. So let's say you consider the Mohr-Coulomb model. So it's a common model for soil. So it considers cohesion, friction angle, and dilation, right? So there is an other model as well, that is Druger-Prager model, which is similar, but it uses a different yield surface. So now a question also arises that if these two models almost resembles, right, then why we should select Mohr-Coulomb plasticity model, and why we should select the Druger-Prager model, right? If you look at here and you look at the models here, then we have this Druger-Prager model, and we also have porous metal plasticity model, we have clay plasticity model, and we have K plasticity model, right? So for the better understanding of your material nature, you will need to select which material you are going to consider for your simulation. So all that depends on the physical phenomena that you want to incorporate in your flexible pavement analysis for the beneath layers of the asphalt concrete. So maybe you would like to include consolidation and critical state concepts in your simulation, which will need these parameters to be decided based on the materials, right? So let me show you that here. If we are, let's suppose, if I open this project 3 and LET theory concept, we sometime deal with the initial states, so in which consolidation is a significant effect in these initial effects, right? So let's wait for that and see what we can do with it, right? Another concept that we are going to discuss here, that's basically the linear elastic model. Let me show you this one. Let's say if I go to the step module here, And if no, let me make this a smaller window. Go back to the discussion which we are doing right now, and let's go to the load, since we are discussing the impact of load as well. And let's say I have this predefined field manager. Here I have a degree of saturation, which is 30.58. And how did I calculate it? Well, actually, if you go to the let me copy that file here. Okay, so I have this another folder. To calculate S4 sile layer, and it's a Python code, so I should yeah, let's forget about it. So let me open this. I actually have written this code using Python, and it was considered to assume these parameters. So yeah, if you look at here, we have the unit weight, saturated unit weight, and dry unit weight is subtracted from it, right? And then the unit weight of water, it is divided with the unit weight of water. So in this particular case that I'm using here, I have a dry unit weight of 19 and a saturated unit weight of 22, and the unit weight of water is 9.81 kilonewton per meter. So when I run this case, actually I got this value here, and that's what I have used here. So in order to consider these key concepts, you actually need to make sure what are you doing in your simulation. So there's another aspect that you should consider when you are considering the soil model for your analysis. So for linear elasticity, let me go back to the previous discussion here. Well, let me try to make it a smaller window here. Okay. So let's say for linear elasticity, a linear elastic model, you actually need only Poisson ratio and Young modulus, while for Mohr-Coulomb model, cohesion, friction angle, dilation angle, and maybe elastic parameters are required. And for Druger-Frager, it would need similar parameters, but with different parameters like in angle of dilation and maybe a different yield criteria. Also for Cain-Clay parameters that required the slope of the critical state line, free consolidation pressure, swelling index, and all these parameters. So all these parameters change with the material of the layer that you are analyzing. So it's another impact. And one thing more, if you have draining conditions and your pavement, whether it is a rigid pavement or whether it is a flexible pavement or semi-rigid pavement, in the multi-layer system, drainage condition is very important. So whether the analysis is drained or undrained affects the material model. So for drain, you might need to consider effective stress parameters and pore pressure, right? So ABAQUS has option for specifying drain if you are using effective stress parameter or undrained with pore pressure effect, right? So maybe using effective stress analysis with appropriate permeability and considering the undrained strain parameter would help you defining the drainage condition in your simulation. So let's say you have drainage condition in your model. So for that you will need, let's suppose if you look at here, here you will need permeability, right, in your simulation. You can also define moisture swelling if there is any moisture swelling in your model, and if you have porous bulk moduli, you also can define it, right? These are the parameters that are important, right? And also for that, maybe if you are using thermal conductivity model, so conductivity and specific heat would be required and heat generation as well. Then we have thermal expansion, which is also required for our model. And if you are using an earthquake analysis model, then damping would definitely play an important role in defining these parameters, right? It's not that much difficult, right? So don't worry about it. It's not difficult. Other than that, what I mentioned, initial conditions like initial stress in soils are also important if you are selecting your soil model. So geostatic stress is important. Initial void ratio and density is also important if you are using a material model. And initial pore pressure if it is a saturated soil. So if you have a saturated soil, you can define the degree of saturation as well. And ABAQUS allows us for these parameters. So if I am, let's suppose I'm talking about the initial stresses, and you are defining your model. So initial stresses, in terms of definition, the initial stress model, it's not related to kind of, property definition, but it's actually a state in your model, which is related to the mechanical load or any other load impact, right? So for initial state, let's go to loads, and here you can define various kinds of initial state which makes sense, right? So let's suppose for initial state here, if I am defining pore pressure here, I can define it. If I have calculated void ratio, I can define them as well, and degree of saturation as well. If we are considering a very rigid pavement with fibers, then we can define material assignment in that direction as well. And if we are considering mechanical loads in the category, then geostatic stress is required. And for geostatic stress, if I try to define it, actually I need to select, let's suppose I need to select a set, and then I will define the magnitude here, which is important in this analysis. So let's go to tool set manager. If I define any set accidentally, so I can delete it. So this is for the geostatic stress that you need to consider. So I defined this. My other point was about the properties definition. So yeah, if you are, for example, if you are considering a density in your model, so that's important. Density is also important. Maybe your model would be elastic, but it would be a dynamic analysis, or you will be studying gravitational force on your model. So for that, the definition will be important for the density, and you will not be able to do that without density, right? So let's suppose if you want to define a geostatic stress and you have density. So if you are defining the loads, and let's suppose you are defining no, not here, here. Let's suppose you are defining a load here, and since I have defined the gravity here as well, if you look at here, and I want to continue with the density, and I define the components here. So I will definitely need gravity here. I will definitely need the density for my analysis. Other than this, permeability and consolidation that I have included here, these are important for initial condition. Hardening and softening laws are also important, and in anisotropy is also important. So nature soil is the soil nature is anisotropic, right? So you should consider these points. And let's say if your model, especially it's not related to soil, it's related to the asphalt concrete as well. Let's suppose if you have asphalt concrete, so rate dependent deformation is very important, and for rate dependent deformation I have mentioned that you can use this tool in your analysis for generating the materials for the asphalt concrete. So other than this, I think I have a lot to discuss in it. Then after that, we need to consider the soil model deformation, right? So I will continue this in the next video.